So you want to be a mathematician? Fantastic. And I agree with you. Mathematics is beautiful. Mathematics is precise. Mathematics is flexible and powerful. It is behind all our technological progress. It can make impossible things possible. It is also a lot of fun. But what does it mean to be a modern-day mathematician? What do mathematicians do? Hello, my name is Dmitry Sevastyanov and I do mathematics at the University of Essex in the UK. Each year, we welcome new applicants who are passionate about mathematics and want to do mathematics with us. But some of our new students are not very sure sometimes how exactly what they learned in maths class can be applied in the real world. How do real mathematicians find those amazing solutions to important and difficult problems? Are these problems in any way similar to what you do in class? What skills do you need to develop to become a modern-day successful mathematician? Here at Essex, we understand how important these questions are for all students studying mathematics. That's why we have a Mathematics Careers and Employability module integrated in all our programs, as well as a professional placement here. We measure our success by success of our students, and we are committed to support them through all their degree. But we also want to reach out to students in schools and colleges. So if you are preparing to your final year exams and consider applying to a university degree in mathematics, this video is for you. Normally, our outreach team will visit as many schools and colleges as possible to talk to students about mathematics as art, as science, and as a profession. We will answer their questions and we will invite them to come back to one of our open days at Essex, ultimately to help them make informed and confident choice about their next step. But it's 2020 and because of the pandemics, we have to do most of the work remotely. So, I would like to discuss a very simple and familiar problem with you, but I will discuss it from a less familiar angle, to show what professional mathematicians have to consider when we solve our problems and how we approach them. Ready? Let's go. Consider this picture here. We have a unit square, a square with side 1, and we have a smaller square, the blue square inside with the side 0.8. My question is, what is the area of this blue square? Do you know the answer? Can you write it down? Of course you can. This is a simple problem really. The answer is 0.64, of course. How do we know this? Well, it's just a basic fact from geometry. Yeah, we know the formula. For every rectangle, and of course a square is also a rectangle, the area is a product of its two sides. So we grab this formula, we plug in the values, which are of course both 0.8, and we multiply them together and produce the answer 0.64. Very nice. So here's another one. We have a red shape here. Can you calculate the area of this red shape? Maybe you need a minute. Pause the video, solve the problem, write down the answer, and come back when you're ready. You did it? Of course, well done. The answer is pi over 4, or numerically 0.7854. A very simple problem again. So you need to recall a basic fact about circles, because this shape is of course a quarter of a circle. So if you have a circle of radius r, the area is pi r square. This is the formula which we remember from our geometry class. And then a little twist here is that we need a quarter of this circle. So because we are talking about a quarter, we need to divide this by 4. And that's how we arrive to this answer after we recognize that the radius is actually 1 and plug in r equal 1. Simple. Okay, so let me challenge you a little bit more. What is the area of this shape now, which is everything which is either in the circle or in the square or in both of them? the area of their union, as we say mathematically, the union of the square and the quadricircle. Pause the video, try to solve this problem. No, seriously, pause the video and try to solve this problem. And even if you don't know how to start, try at least to guess the final answer numerically. Write down some idea of what do you think the answer would be numerically by just looking at this area and trying to estimate, intuitively guess how large it is. Maybe with 1 digit or 2 digits or 3 or 4, how many you can confidently produce. Just write down your best guess. You did it? Okay, I will reveal the answer now. The answer is, the formula is this complicated one, 4 over 25 plus inverse cosine 4 over 5. Numerically, it's 0.8035. So if you guessed even 2 digits correctly, very well done. You have a perfect intuition. If you solved it and got this formula right, even better. Well done. The solution process is, of course, much more complicated. I will sketch it down for you here without much details. If you don't understand something, talk to your geometry teacher, but I will just show how much time it will take me even to write down this solution. Okay, I wrote it down, and as you can probably recognize, even writing it down took me some time. I know my geometry, I know what I'm doing here, I know this particular solution, but it's complicated. It's still complicated. We don't have any formula readily available for the difficult shape which we have, so we have to split it into simpler shapes, like this arc and this triangle. Then we have to recall different formulas for the arc and triangle separately, combine them together, and effectively arrive to the final formula describing the final answer. And of course, your geometry teacher will be very pleased with this work, because you have to recall a lot of facts from different different sides of geometry, and this is really serious analytic work. And by the way, this is called analytic approach to doing mathematics. And this is nice, this is good for you. This is good for training to be a mathematician, because knowing these facts is important. But when we work professionally, when we have to deliver the answer to our client, be it an engineer or an entrepreneur, we won't necessarily need to give them a formula. They are interested in the final answer. Yeah? So maybe all this work, all this nice deductive work of splitting and recombining can be simplified. If we only want to obtain the final answer, maybe there is an alternative way of finding it, which is not so much about the formula. Are you curious to see it? Okay, let's go. Let's play a game. Let's get a handful of random particles, like grains of sand, for example, and throw them inside this unit square. Some of them will end up in this blue square, some of them will end up in a red circle, and normally the larger the area is inside this white square, the more particles will end inside. So because they are random, we can use the number, the quantity of particles inside each area, as an approximation for the size of this area. Yeah? So we can try to estimate all these areas as a fraction of points, random points, which end up inside this area to the total number of points we used in this experiment. And this is the only formula we will need. So we don't care anymore about circles or triangles or rectangles, about geometry. We just care about number of points inside a particular area. We experimentally deduce these areas using only numbers. This is a completely numerical approach. Let's see how it works for us. So if we count the total number of points which are inside this blue area, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 points out of 20, which is approximately 0.7. If I now count the points inside this quarter circle, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which is approximately 0.75. And if I count the total number of points inside the circle or inside the square, it will be 17 out of 20, 0.85. And these numbers are approximations of the areas which you are trying to calculate. If we compare them with the exact areas, if you remember from the previous analytic slide, it was 0.64, 0.78, 0.80, then you will see that these numbers are actually pretty close to the analytic exact answers. So we don't have a formula, but we have a method here of finding these approximate areas. And the good thing about this method is the more points we take, the more accurate these estimates become. Let's do an experiment with much larger number of points, but we of course will need some kind of computer to generate these points for us and to make decisions to count those points which are inside the square and the circle, because we don't want to go through a million points hand by hand. So we will need some sort of computer code. And here, for example, I have a Python code which generates millions of points and then make those decisions which of these points are inside the square, which are inside the circle. So I still need mathematics, but I need mathematics to teach computer how to figure out if the point is inside a particular shape, and as soon as I can teach computer how to figure it out, computer can do the rest of the work for me. So I don't have to explain what this complex shape is in terms of splitting it to basic shapes. I just can instruct my computer to find points which are inside the square or inside the circle. There is a computer syntax for it. And then, if I allow my computer to do it, it will generate the answers for me. And here are the number which computer generates. You can also see them here. And you can probably recognize that they are very, very close to analytical answers which we established before. This means that the method is reliable, we can trust it, we can apply it to different problems, to more complicated problems now. Of course, we appreciate that these values are still approximate, right? We never claim they are exact areas. They are approximate because these experiments are random. Yeah, they are not deterministic. They are random by their nature. So every time we use a slightly different language, for example, if we use MATLAB here with slightly different syntax, it will solve the same problem, but it will generate slightly different random numbers, and these estimates will be slightly different. If I use a statistical language R, for example, I also have slightly different estimates, but they are still quite close to the exact values which we recall from our analytic approach. And if I use, for example, the modern language Julia, then again, it's a slightly different syntax, but essentially it's the same idea, the same comparison, the same mathematics inside, and very close answers. They are very close to other programs, they are also very close to analytic answers, so we can trust these random numbers. They're not completely random, they're just approximate, right? But of course, The puzzling thing is that we don't have a formula here, yeah? Instead of a formula, instead of an analytic answer, a formula which we can plug the values in and calculate the final result, we have a method here. We have a computer program which works as a black box. You plug in some description of shapes and you obtain the values from the random experiment. So it's an experimental mathematics. It's not our analytic mathematics where we manipulate symbols. It's an experimental mathematics where we basically simulate a physical experiment which provides us with the answer. Let's consider this example. We have a unit square, again, we have an inscribed circle inside, and we have two arcs which form the quarter circles here, yeah? And the goal is to find the shadowed area, the area shadowed in green. Try to solve this problem. Pause the video, grab a piece of paper and try to solve it, and come back when you have an answer. Are you here? Do you have an answer? If not, try at least to use your intuition to guess the size of this area. But please make this decision. Write down the size of this area as accurate as you can. You did it? Okay. This is not a simple problem to solve. Actually, it's quite complicated. And it's amazing because it looks like a simple variation of the problem we had before, but even though we have almost the same shapes, we talk about circles, their intersections are now much more complex. So to solve this problem analytically, you need to really spend time on it, yeah? There is a guy on the internet called Presh Talwalkar, I hope I pronounced it correctly. He solved this problem in one of his videos. It took him 5 minutes and 30 seconds even to explain it. And his explanations are very effective. He uses nice videos. He speaks very quickly about everything. So if you actually go to solving this problem, it will take you even more than that. Yeah. But please check his video if you're interested in how to solve it analytically. This is the result he obtained, but his square is of size 10 by 10. My square is 1 by 1, so I need to divide it by 100 to obtain the size of my area here, and it's 0.29276. Yeah. So this is analytic answer. And let's see how much time it will take me now to obtain an approximation of this answer numerically. Let's go. Okay, let me see what this guy is doing, and I will be making comments in real time. So he generates a bunch of random numbers, 1,000 of them, and now he writes a condition which checks if the random point is inside this inscribed circle centered at 0.5, 0.5 with the radius 0.5, hence the numbers in the condition. The second condition is for the quarter circle centered at x equals 1, y equals 0 and the radius 1. The third condition is for another quarter circle centered at x equals 0, y equals 1 and the radius 1. Okay. Now he's writing his main condition to check that the random point is inside the inscribed circle and either outside the first quarter arc or outside the second quarter arc. Okay, that's a complicated condition. He's trying to check it using the plot, but he messed up syntax a little bit. I would never have done it. So it seems like he's recovering, okay? So let's see if his conditions are correct. Yep, it looks like they are, because these random points which pass those conditions form a shape which sort of resembles the shape in question. So now he knows his conditions are correct, and he repeats the same experiments with 100 million points. It takes a little while to generate them, but when they are ready, he just repeats the same checks, the same conditions, and yeah, because he is convinced with them, so he's sure they work. Now the same complex condition here, and a big reveal. What is the area? Wow! It's really very similar to our analytic solution. Impressive! It is time for some final words. What can I say? Mathematics is diverse. Whatever you do in your school or college, whatever your current level of mathematics is, there is always much more to discover. Mathematics is beautiful. Different approaches like analytic and computational approach, they only support each other. Computational numerical methods provide you with quick results which allow you to work with your partners more effectively or to guide your own detective analytic work. Analytical methods are important because they are so ultimate. If you discover a new formula, it may be very difficult, but if you do it, it's a very large and important milestone for development of the whole mathematics. So that's fantastic. Probably what I want to say most of all is do more maths. If you want to continue doing mathematics at the university, if you're curious what we do at the University of Essex, please come to one of our open days, links will be provided in the description, or talk to your mathematical teacher, invite our outreach team to visit your school or college. We can visit you distantly, we can visit you face to face if it's safe or when it's safe. So please find our contact details in the description and get in touch. Do more mathematics, enjoy what you are doing, stay safe, and have a lovely day. Bye.